Hi, this is Mrs. Verbal. This is Chapter 12, States of Matter, Part 1. So today we're going to be talking about gases, and I have a couple examples of gases here. So I have my favorite perfume, and I'm going to ask you what this is in a little bit. And then I also have a balloon here. So the question is, I'm going to ask you what this is. So looking at solids, liquids, and gases, we're going to investigate what is the macroscopic differences between them. In this chapter, we're going to look at what are the molecular interactions that cause this difference. And then we're going to also look at the changes that have to occur at the molecular level to move between the different phases. And then lastly, we're going to look at energy changes. So we need to examine what happens to energy when we move between solid, liquids, or gases. So I have three examples of gases, liquids, and solids, different phases. And notice that the molecules, the way they're drawn, they assume a certain movement. And if you had to guess which one has the most movement, correct. So gases tend to have the most movement as opposed to solids. So we're going to look at the gases and the kinetic behavior of them. And in order to understand their behavior, we're going to assume some things. They may seem a little strange, but it helps us to understand their behavior better. So notice that we say that all gases have tiny particles. And when we look at those tiny particles, they're essentially molecules. So it could be water, it could be oxygen, it could be nitrogen. Please note that these molecules are in constant movement. They do not necessarily stop moving. Their movement causes them to be far apart. So think about them being just like your relatives that cannot stand each other. They're going to occupy opposite corners of the room just so they can be as far apart away from each other. And gas molecules do the same thing. And then lastly, we're looking at temperature. So temperature, notice if the temperature decreases, the velocity decreases. Therefore, the kinetic energy goes down. And that makes sense. There's less movement, so there's actually less energy that's involved with that molecule. Well, there's actually two more postulates that we're going to add to this, and these are postulates that you're going to need to know. Here we're saying that molecules are perfectly elastic. So if you wanted to assume that water molecules are just like a red rubber ball, they essentially, when they collide with each other, do not lose any energy. So they retain their energy. Now, this last statement I haven't read is because we tend to ignore the fact that there's attractive forces, and we'll talk more specifically about those forces. We're assuming that these molecules, they like each other, they kind of stick to each other based on their attractive forces, and we'll talk more about that later. Here is another summary of the kinetic molecular theories. These are just a restating of the previous six. That's all I want to say about that. Okay, so why do we want to know? Well, it's good to understand the behavior of gases so we can predict what happens when we do something with them. You may notice that in the summertime, your tires are going to be inflated differently than in the wintertime. The other thing is you may notice with gases that you can actually push the gas together, but with liquids you can't. And the question is, how come? And then lastly, in the beginning, I showed you my perfume bottle. How can you smell the perfume that somebody had just put on maybe about 50 feet away from you? So because of these questions, we have ideas, and we can explain that using the kinetic molecular theory. Now, you might think about it this way. Gases, the reason why they're able to do what they do is because there's not a whole lot causing them to stay together. So the attraction is low. So because the attraction is low, they have what we call diffusion. So diffusion is essentially one set of material that moves past another. So it could be a mixing of two different gases, maybe oxygen and hydrogen. Now, when I was blowing up that balloon, what you may not have realized, but essentially I was doing effusion by letting that balloon go. So I was letting a small opening occur in that balloon, and that forced the gases to escape out of that balloon, which projected it in another direction. So whenever we talk about effusion, we're talking about a hole in a container. Okay, so you're going to be doing some calculations in the classroom, and we use what we call Graham's law of effusion. And with Graham's law of effusion, this is just based on one material. Notice that the rate, and this little symbol here is, it approximates the square root of the molar mass. And notice it's 1 over the square root. So there's sort of a diagonal relationship between these two. So you're going to calculate the molar mass using the periodic table, and when you take the 1 over the square root of that, you're going to get the rate. We could actually apply this to two different molecules. Now, I want you to pay attention here. So notice A is diagonally located with molar mass of A over here, and B is diagonally related to the molar mass of B over here. Notice that both of them are underneath the square root. So when you're looking at the rate of A, the square root of the molar mass of A is in the denominator, and the rate of B, the square mass, molar mass, is in the numerator. So make sure you pay attention to that when you do those types of calculations.